Hi, everyone. My name is Letisha Smith. I'm a data scientist at Teachers Pay Teachers. And today I'll be talking about a personal project that I've been working on to identify groups of recipes that share similar ingredients, and I'll be sharing lessons that I've learned along the way. So for background, I got started on this project at the beginning of the year when I made the resolution to eat healthier. However, after checking out a few fad diets in addition to recommended nutrition guidelines, I started to recognize a common flaw in the weekly eating guides. One day you may have lasagna for dinner, the next day you have curry. Each one of these dishes requires a unique combination of ingredients that will go to waste if not entirely used in its dish. Now, traditionally we solve this problem by Googling recipes that use leftover ingredients. However, this approach is reactive, not proactive. So I wanted to see if I could leverage machine learning in order to identify groups of recipes with shared ingredients in order to maximize the number of meals I can make with the minimal amount of ingredients. With my research question defined, it was time for me to collect my data, which is where I learned my first lesson. Be kind to your host, which for me was allrecipes.com. So I wanted to scrape and analyze the ingredients found in dishes on allrecipes.com because it's arguably one of the most popular recipe sites on the internet. It was founded in 1997, and what really made this website distinct from a lot of other recipe websites at the time is that it had a strong community of users who would leave reviews for the recipes. So if you look to the right, or I guess it's my right, but your left, is World's Best Lasagna. And that's the most popular recipe in the main meal section of the website, and it has over 11,000 views. So this really helped to verify that these recipes that I was looking at were contained ingredients that were of high quality. And I focused specifically on main meals just because those are the types of dishes that you would prepare during mealtime or during dinner time, which is when I think that meal prep is most important. However, before I had the opportunity to scrape and analyze all of this data, I found myself sending the following text message to a friend, which I'll give you all a moment to read. So no, the site didn't know that I needed the information for a project because I was scraping this data. When you scrape data, your requests to the site travel at a faster rate than when you're typing information into a search bar and then pressing a button. And because of that, there were so many requests that were going to the server, and the server wasn't having enough time to respond. So it just basically felt like it was under attack and essentially stopped working. So what this experience taught me is that if you do choose to scrape data from a website, you should check to see if the website has a robots.txt file, which contains useful information such as having a 1-second crawl delay in between your requests just so the server has enough time to respond. The last time that I scraped this website was in May of last year. At that point in time, the website had 14,000 recipes in the main meal section, which was essentially 165 pages. So after 6 hours, I was able to collect all of this data. And it was time for me to learn my second lesson, which may be common to the statisticians here, which is data analysis is like healthy eating, garbage in, garbage out. So like I said, I really wanted to identify the very best recipes that this website had to offer. So my first step was taking a look at the average number of stars that the recipes receive. So I have a histogram to show you. And if you look on the x-axis of this histogram, you'll see that it ranges from 0 to 5, 5 being the highest number of stars that a recipe can receive. And the bin width for this histogram is 0.25, so if you look on the left from 0 to 0.25, approximately like 1,000 recipes on the site haven't been reviewed. And one thing that really surprised me when looking at the data is that this histogram, for the most part, has a negative skew. And the mean or the average number of stars that a recipe has received, or their average star score, is 4. So on average, recipes on this site do receive a favorable number of reviews, and I decided that I just wanted to limit the analysis to recipes that had received at least 4.5 stars. That way I could at least say that it was above average star score. But the one problem with that is I don't know if this is a recipe like World's Best Lasagna that's received like thousands and thousands of reviews, or if this is this recipe that's been recently uploaded to the site, maybe where there's only 3 or 4 reviews. So I also want to look at the total number of reviews that recipes on the site had received. So I have 2 histograms to show you. The first one represents 90% of the recipes in the main meals section. So this is all but like the top 10%. And the reason that I put all of these in the first histogram is you'll see that the histogram has a positive skew. And the x-axis goes from 0 to 200. So anything after 200 just start to be too low to view in this histogram, which is why I saved it for the second one that I'll share. And the bandwidth here is 10. So if you look on the x-axis between 0 and 10, you'll see that I think it's like approximately 4,500 recipes. They've received 0 to 10 reviews. And then if you make your way over, on average, recipes on the site have received around 90 reviews. And then for my second histogram, this is the top 10% of recipes. Then you'll see that it ranges from 200 to almost 1,200. And the bandwidth is 500, so if you look from like 200 to 500, you'll see that around 200 to 500 recipes have received almost 1,100 reviews. So after looking at this data, I decided that I really want to focus on the 130 region, because recipes that had received like around 130 reviews, that sort of represents like the top 15% of recipes on that site. So to recap, I wanted to look at recipes that had at least 4.5 stars, 130 reviews, which narrowed the analysis to around 909 recipes. So now that I have the data, I have a snapshot to show you of what it looked like. So you'll see like it's not nicely formatted, but even though the format doesn't look nice, we as humans still like know what the recipes are. So like if you look at number 4, go down to number 2, you'll see like the second ingredient is vegetable oil. Very easy for a human to understand, but not so easy for a computer to understand. So when you're processing text, one of the common approaches is treating your text as a bag of words. So when you do that, you remove numbers and punctuation, you remove the endings of words like ed, ing that aren't as essential, and you also, let's see, ed, ing, and you also remove stop words. So these are words that are common like the, or, a, that don't really provide me any additional information about the context. So that's what I did with this data here, to get a sense of what these common food words were. And this is the word cloud that I got. So you can see G for grams. Maybe you're lucky to see ml for milliliters. And I know there are like some words like chopped in there too. But I was looking for food words, but I was getting words related to units of measurement, also words related to food preparation. So I had to take a step back and think like there are all of these non-essential words here. So I had 2 approaches. One of them was I could create a corpus of stop words related to recipes and extract those words or remove those words beforehand and then redo my word cloud. But at best, like that would just take a lot of time trying to get that corpus together. But at worst, I could possibly like bias my results by choosing which words are and are not essential. So instead, I decided that I really needed to identify like what were the food words. That way, if I knew what the food words were, then maybe I could just look at a recipe and say, if a recipe has this food, then like a check. So the example I like to give is like, irregardless of whether or not a recipe has like fresh green beans or canned green beans or frozen green beans, I just really want to know that it had green beans. So what I ended up doing is I collected a list of food words. So I got this list from going to a variety of sites that have food words so that I could then create a matrix that I'll show you here. And what I did was I just put the food words in the columns here. And then for each row, I put a recipe. And if the recipe contained that food word, then I put a 1 in the column indicating that the food was there. And that allowed me to transfer this text data that I had into a format that was easy to feed into a computer. And I have another word cloud here. And now you'll see in my word cloud, I actually have food words. And now that I had my data clean, it was time for me to learn my final lesson, which is to measure carefully but season to taste. So like I said, I really wanted to identify which recipes were closest to one another, which implies that I needed to use a distance metric. And in R, there are a lot of different distance metrics. And if you use the wrong one, then it will produce misleading results. So what I have on the following slide is what my data looked like when I did not use the proper distance metric. I just used the default metric, which is Euclidean distance. So what I have up here is a dendrogram. And it's a graphical representation of hierarchical clustering, which is a bottom-up clustering algorithm. And for those of you who are unfamiliar with it, the way that it works is essentially each item, which for me were recipes, are placed into a group of its own. And then the items are incrementally paired based upon how similar they are until they all end up in an individual group, which is really difficult to see here because I use Euclidean, like I said, which is the default, and wasn't really great for this data. But I played around, and another popular distance metric is Manhattan distance. I changed my distance metric, and now you start to see structure, kind of like what you would see maybe if you're looking at some sort of animal kingdom diagram. And so at this point, I had measured properly, and now it was time for me to season to taste. So I like to think of statistics as part science, part art. When you do statistics, there are assumptions, and there are steps that you need to make sure that you take in order to like meet whatever statistical standards for the method that it is that you're using. And like for me, that's hierarchical clustering. But I feel like the art really comes with regards to the interpretation of your results, because you do want to make sure that your results make sense. And for hierarchical clustering, like I said, it's great because all of your items do end up getting paired, but one downside is that they all end up in a single group, because you'll see at the top I have this line that's connecting everything together. But I was really looking for individual groups. And for hierarchical clustering, there are different metrics that you can use to identify like what are the best number of divisions that I can make. So I'll just like stand over here real quick to show like you can cut at the top right here across, and then you can have 2 groups. And I was consistently told like my data was best represented by 2 groups, but that didn't work. So I needed to like dig a little bit deeper in the data. So maybe like do 3 cuts, 1, 2, 3, like 3 divisions, or 4. And then whenever I made these divisions, I would then look at the groups to see like what recipes are there, what ingredients are being used, to see if the groups that I had made sense. And after playing around with the data and digging into it, I was able to determine that my data could be meaningfully represented in 11 groups, which I have here for you to see. So Pan-Asian, barbecue, slow-cooked poultry, savory pie, marinade, Italian, Tex-Mex, breadcrumbs, veggies, and shrimp. And I'll like go into some of those groups in a little bit, but just so you can see, like, if you look down low enough, you'll see how I made the cuts to identify those 11 groups. All right, so after I had presented some of these results, I had people ask me questions such as, okay, look, you have these 11 groups, like, but what do those 11 groups actually mean if I wanted to use them in my day-to-day cooking? So I thought of it, and then I have like one little bonus tip, which is don't be afraid to sample along the way. So after I got these questions, I like sort of did a thought experiment in my head, and I asked myself, what would happen if I were to randomly select 3 recipes from a group? And after I randomly sampled those 3 recipes, I want to find the percentage of the ingredients that are used in more than one dish. And what would happen if I repeated that process 10,000 times? So I'm going to show you what that looks like, in addition to showing you all what some of the food words in the group were in these groups, in addition to some of the different recipes. Okay. So I completed the experiment with all of the recipes first. So like I said, pool 3, see what % are used in more than one recipe, and on average you expect for 16% of the ingredients to be used in more than one dish. And then I have the shrimp group here. So to my right, your left, there's a word cloud of some of the common food words, and then if we look at the histogram, we'll see that if you were to randomly select 3 recipes from the shrimp group, you would expect on average for 36% of the ingredients to be used in more than one recipe, or yeah, in more than one dish. And here's an example of some of the recipes that are in that group. Okay, next is this Breadcrumb Group. And to provide some context, the Breadcrumb Group is really for recipes where either you're making like some type of patty or maybe you're frying something, which is why the breadcrumbs were so prominent, along with other foods such as eggs that you use for that process. And here are some of the examples of the recipes. Next is the Chicken Broth Group. So you can look. And here are some examples. Next is the Barbecue Group. And the last one that I show is the Pan-Asian Group. So this one was pretty cool just because of that commonality of soy sauce really helped to unite those recipes together. All right, so next steps. I thought this was like a really cool project just because I felt like I was able to identify the groups of recipes that shared similar ingredients without having to pre-specify foods up front. One thing that I will say though is that some of these groups are like kind of intuitive. For instance, like if I want to make Tex-Mex, maybe I like don't necessarily have to choose specific ones from that Tex-Mex group, but I started to realize that either the groups are representative of cuisines, but also some of the proteins played a very heavy role in identifying those groups. So since some of them are a bit intuitive, I think in the future, maybe trying to play around with maybe removing some of those protein words to see like what type of groups do I then get, or sometimes words like salt are common throughout the group, so like what would my groups look like if I were to remove some of those core staples. So in conclusion, when cooking up statistics, remember to be kind to your host, garbage in, garbage out, and to measure carefully, but to season to taste. I think, yep, and thank you.